Okay, we're into Module 6. Now, Module 6, we actually have two chapters we're going to cover. We're going to be talking about how chemicals react, and that means chapters 20 and 21 in your book. And if you notice, the first thing in chapter 20 is a little explore activity. And what they tell you to do is to get yourself 2 cups of water and make it kind of lukewarm water. Now, one thing that's very important is to, first of all, you want to mix the cups. You want to make sure that the temperature of the water is the same for each cup. So mix them several times so that we can pretty well guarantee that each cup has the same temperature water, and make sure your levels are about the same. And you can test it on your cheeks to make sure that the temperature is about the same. That's pretty good. Now you're instructed to get some salt and pour several tablespoons of salt into one of the cups. And we'll mix it around a little bit. If you recall from last module, we can talk like chemists. We can say the salt is the solute, the water is the solvent, and we're making a salt water solution. And once you are, hopefully I've not saturated the solution. If I saturated the solution, I might have some precipitate at the bottom of the cup. So now that you're a chemist, you understand your jargon. But after you've done this, then you test the temperature. You check the temperature of each cup on your cheek. And, well, I'm not going to tell you what I just discovered. You're going to do this on your own, aren't you? You don't get physically fit by watching someone else do push-ups, do you? So that's your assignment. Try this at home, and then we're going to tackle the Module 6 materials. Okay, so I hope you've checked out the chapter titles of both of these chapters. Chapter 20 is how chemicals react. Then chapter 21 is 2 types of chemical reactions. So we're talking about chemical reactions in this module. Now, what is a reaction? It's essentially when one or more compounds, new compounds, are formed as a result of other compounds or atoms reacting. Okay, so in this case, we have 2 hydrogen molecules, molecular hydrogen. Okay, it's a molecular hydrogen because you got a hydrogen atom here, hydrogen atom here. They are bound to each other. And you react them with an oxygen molecule. 2 oxygens linked together. And what you wind up with is something entirely new. Right? These are new products. Right? Here we have 2 blues linked. Here we have two reds linked. Now all of a sudden we wind up with a red linked with 2 blues, and another red linked with 2 blues. These are 2 water molecules because we have 2 hydrogens attached to the 1 oxygen. So this is a chemical reaction. Now notice a couple of things. First of all, we have what are called subscripts. That little 2 here is called a subscript. That indicates that you have 2 oxygen atoms linked together or 2 hydrogen atoms linked together. The 2 out front here is what's called a coefficient because I have 2 of these hydrogen molecules. Notice that I have just 1 oxygen molecule. Usually the 1 is not it's just understood. So quite often the 1 is not even written in a chemical equation. And then we wind up with 2 H2Os because for this water molecule, I've got 2 hydrogens linked with 1 oxygen. So I've got 2 hydrogens linked with 1 oxygen. Notice that the 1 is also not written. It's understood that I only have 1 oxygen in this molecule. And notice that I've got the coefficient out front here because I've got 2 water molecules created out of this reaction. Now, last thing to notice is that how many reds do I have on the left side of the equation? 2, right? How many reds do I have on the right side of the equation? 1, 2. How many blues do I have on the left side of the equation? 1, 2, 3, 4. How many blues do I have on the right side of the equation? 1, 2, 3, 4. That's a very important result. What that tells us is that there is a law of mass conservation that is obeyed in a chemical equation. No atoms are gained or lost during any reaction. I started out with 2 oxygens and 4 hydrogens, and I wound up with 2 oxygens, 4 hydrogens. The only thing that changed was the way they were arranged, the way they were perhaps bound together. So the number of times that atoms appear before the arrow must be equal to the number of times that they appear after the arrow. That is the law of mass conservation that is indeed obeyed in all chemical reactions. Okay, now this portion of the notes is a little bit of a diversion from what the book covers. The book actually speeds through this, but this is actually a review of something we covered in last chapter or last module about molar mass. So when we have a chemical equation, notice we have reactants on the left side, we've got products on the right side, and if you recall, we made the distinction last time between atomic mass, which is usually given in the periodic table as this little number here. That's the mass of one atom given in atomic mass units. So for example, carbon has 6 protons, 6 neutrons. Each of those has essentially, each proton or each neutron has approximately 1 atomic mass unit. And therefore you wind up with 6 and 6 is 12. And again, why is it not exactly 12? Well, because there's several different isotopes of carbon, which occur with different percentages in nature, and so the average gives you an atomic mass of 12.011. That's the mass of one carbon atom. Again, that's one atom, really, really, really small. When we want to talk about a macroscopic sample of carbon, we have to think about a whole mole of carbon. Remember, that's 6.02 times 10 to the 23rd atoms. And it turns out that the mass of an entire mole of carbon would be 12 grams. So molar mass is always given in grams. Similarly with oxygen, in the case of an oxygen molecule, that's 2 oxygen atoms together. Notice the atomic mass of one single atom is around 16, so therefore the mass of an oxygen molecule is 32 AMUs. An entire mole of oxygen molecules would be around 32 grams. So notice when we compare the relative masses, the mass of a single carbon atom is 12. The mass of a oxygen molecule is 32, and therefore the ratio is 3/8. So carbon is 3/8 as massive as an oxygen molecule, whether you consider one atom or if you consider an entire mole of either one. That's an important point to recall. So remember that Avogadro's number, this huge number, 6.02 times 10 to the 23rd, this is a way of expressing the mass of an entire, a huge collection, 6.02 times 10 to the 23rd. So that, for example, sodium. One entire mole of sodium atoms has a mass of about 23 grams. Lead is even more massive per atom, so therefore this huge collection of them would have a mass of 207.2 grams. And helium, one of the lighter elements, an entire mole of helium atoms has a mass of only 4.003 grams. So now that we remember what molar mass is, this gives us a little more insight when we look at a chemical equation. So for example, our original example of 2 hydrogen molecules combining with 1 oxygen molecule giving us 2 molecules of water. We can now view this on the microscopic level. We can think about it as being, okay, well, 2 hydrogen molecules and 1 oxygen molecule giving us 2 molecules of water. But we can also look on a macroscopic level and think, okay, well, this is no different than 2 moles. That's a huge number of, in fact, it's this number of hydrogen molecules combining with this huge number of oxygen molecules will give us this number of water molecules. So you can view it on a molar level, a macroscopic level, and of course recognize that we can talk about the molar mass, which is another way of saying 4 grams of hydrogen, molecular hydrogen, and if we mix that with 32 grams of molecular oxygen, will result in 36 grams of water. Okay, so now that you know what a chemical equation is, and you know what the law of mass conservation is, you should go ahead and take a swing at the skills test entitled Balancing Chemical Equations. It is a PhET simulation. In order to get familiar with the interface, you may want to check out the video tutorial, which will help you step through the process. Okay, now that we know what a chemical reaction is, we can balance chemical reactions or chemical equations. Let's have an example of a chemical reaction. What's going on here? I've got cellulose in this matchstick, and in the presence of oxygen, it is creating energy, and I'm also getting a byproduct like carbon dioxide and such. Now, this is a chemical reaction. I've got products, I've got reactants. How could I have made that reaction increase in its rate? How could that reaction, that combustion reaction, have happened faster? What if I had, instead of just having this room full of air, what if I was in a room full of oxygen? What would have happened then? I would have had an explosion. I would have had a really fast reaction. So it turns out that reactions can proceed at different speeds depending upon the conditions. And some of the conditions that we can change are the concentrations. And again, if I was in a room of oxygen, I would have changed the concentration of oxygen molecules available for that combustion reaction. Temperature, as well as the presence of catalysts, can also affect the rate of your reaction as well. So for example, again, concentration. In order to have combustion, I need to have oxygen molecules available. If I've got more oxygen molecules, I can have more reactions. More reactions means more energy liberated during combustion. Temperature can also affect the rate of reaction. As the molecules move around faster, they're more likely to run into the ones that they need to combine with in order to make the reaction occur. So again, quite often temperature will increase. The higher the temperature, quite often, the greater the reaction rate. Which is why when you put stuff in refrigerators to keep your produce fresh. Why is that? Because when your produce rots, it's essentially having new chemical reactions are occurring. In order to slow the rate of chemical reactions, you have to cool them down. Another thing is catalysts. So read about catalysts. Catalysts are essentially middlemen, required chemicals that will make reactions occur. Because quite often, in this example, we got nitrogen, we got oxygen, and when they form nitrogen monoxide, the energy is actually higher. So you need to get over this little hump here, this energy hump. It's called an activation energy. So quite often you need something to help out kind of a middleman. That quite often will lower the energy hump that has to be climbed in order to make the reaction occur. Okay, so section 20.4 in your book is about endothermic and exothermic reactions. And you should be aware of the fact that in a chemical reaction, the reactants quite often are broken apart. And then the atoms are rearranged and you wind up with the products. When you break bonds apart, when you break chemical bonds apart, it usually takes energy. So in the reactant side of things, it's going to take energy to create, or to break apart the reactants. And when the products form, usually bonds are formed or created, usually energy is liberated. The question is, how much energy goes into the breaking of the bonds on the reactant side compared to how much energy is liberated in the forming of bonds on the product side? If there's overall a net production of energy, we call that an exothermic reaction. If, however, it takes energy if there's more energy required to break up the bonds than is liberated in the formation of bonds on the product side, we call that an endothermic reaction. And this chart from your book will be useful, in fact it's on page 450, useful in helping you determine whether an overall reaction is endothermic or exothermic. The final section of this chapter, chapter 20, is about entropy. It's section 20.5, and essentially what it says is that energy tends to go from being in a more concentrated form to a less concentrated form. That's just the way nature works. It goes from being very high energy to less concentrated energy. For example, a hot pan. Once it gets hot, you heat it on the stove, you've got a pan of hot water, turn off the heat and just, what happens to that hot pan? Does it stay hot? Because when you got a pot of hot water, that's a lot of energy concentrated in a small area. What happens to that pan eventually? It eventually cools down to room temperature. Well, what happened to that energy? It didn't just disappear. Energy isn't just destroyed, but what happened? The air around the pot got heated because it was close to the pot. And then what did that air do? Well, it was by being hotter, it was less dense, and therefore it rose, and it gave off, and essentially, if you had a sensitive enough thermometer, you would discover that from that hot pot of water, you would actually wind up heating the air of the room. And of course, that air, wound up circulating elsewhere and giving off its energy. But essentially, the long and the short is that in a natural process, the energy goes from being in a more concentrated form to a less concentrated form. Gasoline. Gasoline is just essentially a very concentrated form of energy. You combust it, and what happens? It explodes, right? It creates a gas that expands really quickly, and it helps to push the cylinders in your car and drive your wheels forward. What also happens to that energy? It goes out the back of your tailpipe and into the atmosphere and heats up that air. But can you ever get that energy back? No. And the same thing with a hot pan, right? You can't go back and reclaim all that energy that was lost to the air in the room. No. If you want your water hot again, you have to use brand new energy, such as the stove, and turn it back on. Same thing with even marbles. If you have a nice jar of marbles, it's all concentrated, and then all of a sudden you turn them upside down and let them bounce on the floor. Well, what happens? All that energy of motion, eventually those marbles come to a stop. And where did that energy go? It went into the sound that was produced. It went into perhaps the heating, as those marbles hit the floor. It made the tile molecules move around a little bit more. You can never reclaim all that energy. You can never go back in order to get the marbles back into place and pick them back up onto the desk. You have to use new energy from your muscles to reorganize them, put them back in the jar. You have to lift them back up onto the desk. So entropy, that is the degree to which energy has become dispersed. Things usually go from having little entropy to a lot of entropy. So being very, very concentrated energy to less concentrated energy. Now, as we already mentioned, entropy is the amount of disorder. So if you go from a situation where you have very little disorder to much greater disorder, or more concentration of energy to less concentration of energy, that's kind of the natural way of things. And if you have a reaction that proceeds in that way, such as an exothermic reaction, then you don't have to add any energy to that system. It's going to be self-sustaining. So, for example, a campfire. Once you get it started, it kind of goes on its own because it's an exothermic reaction. As you go from a more concentrated form of energy, such as the cellulose of the wood, to the carbon dioxide and the byproducts of combustion, it doesn't take once you get the thing started. You don't need to continue to constantly light the fire again. That's different than, say, an endothermic reaction like photosynthesis. Photosynthesis, in order to take carbon dioxide and water and create cellulose out of those reactants, you need to have a constant supply of energy because you're going from a less organized form of energy to a more organized form of energy, and therefore we call that an endothermic reaction. Okay, so now we dive into chapter 21, which describes two different types of reactions. We're going to talk about acid-base reactions as well as oxidation-reduction reactions. First of all, let's focus on the acid-base stuff. Of course, here's an example of several common acids. Right? You've got citric acid in many of the fruits. You've got carbonic acid in sodas. So here's some examples of everyday objects that have, or everyday products that have acids, and then these are bases here: baking soda, drain cleaner, ash from a fire, soap. Those are bases. So chemically, what's going on? What is an acid? What's a base? An acid is a chemical that donates a hydrogen ion. A base is a chemical that accepts a hydrogen ion. Now we're going to give you a little acronym or a little mnemonic device that's going to help you remember that. Let's see this in action. Now, first of all, what's a hydrogen ion? In order to understand a hydrogen ion, we have to understand what a hydrogen atom is, the simplest of all elements. Remember, hydrogen has an atomic number of 1. That means it's got 1 proton in its nucleus, and no neutrons. So the nucleus is very simple, just a proton. And an uncharged hydrogen atom, in order to be uncharged, we need to have an electron as well. So a simple hydrogen atom has a proton in its nucleus, an electron outside the nucleus in the electron cloud, and that's it. So therefore, overall, uncharged. What's a hydrogen ion then? Hydrogen ion is a hydrogen atom that has been stripped of its electron. So now if you take away the electron, what do we have? We have a positively charged atom. And as if you recall, the definition of an ion is a positively or negatively charged atom. So we have the hydrogen ion. We just have a single proton and nothing else. And it's usually written as H+. So quite often, if you see that H+, that's indicative of a hydrogen ion. It's the same thing. And it's the same thing, it's essentially just a proton. That's all it is. So now here's your mnemonic device. Bases accept, acids donate. Okay, bases accept, acids donate. So let's take, for example, hydrochloric acid, HCl. Well, you sort of know that it's going to be the acid, right? When we put it in water, here's what happens. The hydrogen from the hydrogen chloride leaves, and it joins the water. So you wind up having what used to be HCl now is just chlorine, this hydrochloric molecule that has been stripped away, that has donated a hydrogen ion. It's donated a proton, right? That proton went over to the water. So now we have essentially a negative molecule here, chlorine having been stripped of a proton, and you have now water that has an extra proton attached to it because it accepts that hydrogen atom or that hydrogen ion. So you have what's called the hydronium ion, H3O+. Again, because this was HCl, but all of a sudden, boom, it lost a positive. So therefore, the Cl ion is negative, and the water accepted an extra proton, so it became H30 or H3O, and of course, having that extra proton makes it a positive molecule. So, what happened? The hydrochloric acid donated a proton. Remember, bases accept, acids donate. So therefore, that's why we call the hydrochloric acid here, we call it an acid because it donates a proton. The water accepts the proton and becomes the hydronium ion. Okay, another example. Again, these are given in your book on page 462, 463. So now we've got water and we've got ammonia. So what happens? The water donates a proton to the ammonia. So you wind up with a hydroxide ion, OH with a negative sign, because again, it's donated a positive charge. It donated a proton. So therefore now this ion is negatively charged. The ammonia accepted a proton. So it's got an extra hydrogen here. So that's why it went from being NH3 to NH4. And notice the sign here. It's positive because it's got one extra charge to it. Now, this is a two-way street. It turns out that with these two chemicals, they can actually play different roles. So it turns out that when we're going in this direction, the water donates the proton to the ammonia, and therefore we would say that the water is acting as the donor there, and therefore it's the acid, because again, acids donate, bases accept. So in this case, the ammonia is acting as the base because it's accepting the proton, and therefore you wind up with the hydronium ion and the hydronium ion. I'm sorry, the hydroxide ion, OH negative, and the ammonium ion, NH4 positive. But it turns out that things can actually go the other way as well. The ammonium ion can donate a proton to the hydroxide ion, in which case it acts as an acid. It donates. The hydroxide ion, OH negative, acts as the base there, and then can reform the original water and your ammonia. So we have, in this case, this is a two-way street, a two-way reaction. Either you can go from having water and ammonia producing the hydroxide ion and the ammonium ion, in which case the water acts as a base because it's donated a proton. The ammonia the water acts as an acid, it's donated a proton. The ammonia acts as a base because it accepts the proton, and you produce these two products. Or these can be your reactants, and you can use these as the products, in which case the ammonium ion acts like an acid because it's going to donate a proton to the hydroxide ion, which is then going to form these other products. So it's actually this is a reversible reaction. So your left side can produce the right side, but the right side can also produce the left side. Okay, at the tail end of section 21.1, the book talks about the definition of a salt. We think about salt as being stuff you put on your popcorn, but a salt can be really any compound that's formed from the reaction of an acid and a base. So we know of sodium chloride, that's the one we're most familiar with, but it turns out that there's actually a number of different salts when we talk about chemistry. There's sodium cyanide, there's potassium nitrate. These are all salts. Calcium chloride, sodium fluoride, they're all salts because they are the result, they're the product of the reaction of an acid and a base. So when you have hydrogen cyanide combining with sodium hydroxide, you wind up with sodium cyanide. That's the salt. Now notice that quite often when a salt is formed, water is a byproduct. That's not always the case, but it is relatively common. So quite often you do have water as being the byproduct. As described on page 466, here is a situation where you have a salt being formed, this pseudoephedrine hydrochloride. The salt is being formed without water being a byproduct. So you take hydrogen chloride and pseudoephedrine. The hydrogen chloride donates a proton. The pseudoephedrine accepts the proton. Therefore, the hydrogen chloride acts like an acid, pseudoephedrine acts like a base, and then your product winds up being the salt, pseudoephedrine hydrochloride. Okay, section 21.2 gets into the strength, the relative strengths of acids and bases. And it says that strong acids and bases ionize completely in water. So remember what that means. That means that for an acid, acids donate protons. So if you put an acid in water and see what happens to that acid, does it ionize? Does it actually break apart? Does it donate its proton to the water molecules, therefore producing hydronium ions? So for example, here we have hydrogen chloride, HCl, and the reactants are on this side, and here's a little sample of, microscopic sample of the solution. And what do you see? Do you see any hydrogen chloride? I don't. Right, here's your hydrogen chloride, a green and a blue. Do you see any greens and blues in here? No. I see a lot of just plain old greens, but I don't see any greens and blues. This tells me that the hydrogen chloride, all of the hydrogen chloride molecules gave up their protons to water molecules in order to produce the hydronium ions. I see plenty of hydronium ions. I see plenty of chloride ions, which tells me that this hydrogen chloride did act as an acid, and it is a strong acid because it completely ionized in the water. I don't see any unreacted hydrogen chloride kicking around here. All of the hydrogen chloride broke up, donated protons to water, so therefore we would judge hydrogen chloride to be a strong acid here. Acids donate. Now, let's take another example. Acetic acid, C2H4O2. We combine that in water. Here's the microscopic result. What do you see? Well, I see an acetate ion right here. That is one where, again, a proton was donated. And so I went from having acetic acid to having an acetate ion. Remember, I gave up a positive charge, so therefore the ion is negatively charged. But I also see a completely intact acetic acid molecule. Here I see another one. So these ones did not donate. Only this one wound up donating and producing the acetate ion. And so therefore I don't see that many hydronium ions either. So this would be a weak acid. Yes, it does behave as an acid. The acetic acid does indeed donate, but not every molecule of acetic acid donates. a relative few donate, and therefore this would be classified as a weak acid. In section 21.3, the early part of the section discusses water and the fact that water can actually react with itself. It can donate protons, such as here, this particular water molecule is donating a proton to this water molecule, and therefore you have the formation of a hydroxide ion and a hydronium ion. So what is water? Is it an acid or is it a base? Well, it turns out it's actually both, because here I've got water that's donating a proton. Remember, acids donate, but I've also got a water molecule here that's accepting a proton, so it acts as a base. So I actually have one molecule acting like an acid, one molecule acting like a base. And it turns out that this doesn't happen that often. So as is mentioned in the early part of section 21.3, the number of water molecules that are actually donating or accepting protons is relatively few, and therefore water would be classified as either a really weak acid or a really weak base at the same time, because you can't have a proton being donated without one being accepted. You've probably heard of the pH scale. It's just a logarithmic scale indicating the relative ratios of hydronium ions to hydroxide ions. As we just discussed in water, typically water molecules don't donate or accept, but when they do, for every acceptor, you have a donor. And therefore the hydronium concentration, the concentration of hydronium ions is the same as the concentration of hydroxide ions. And therefore, when we have this balance, we say that it's got a pH of 7. So it's a neutral solution. Now, if you have a solution where you have more hydronium ions than you do hydroxide ions, we would say this is an acidic solution. It's going to have a pH that is less than 7. The hydronium ions outweigh, or there's more of them than the hydroxide ions. Opposite, if you have hydronium ions that are fewer in number than hydroxide ions, we say that this is a basic solution, and you're going to have a pH somewhere higher than 7, between 7 and 14. Okay, so if you only get as far as understanding the relative ratios of hydronium ions to hydroxide ions and how that results in either an acidic or a basic solution, you're probably going to be all right. But if you want to dig a little deeper and understand the pH scale, check out pages 470 and especially the box on 471 that talks about logarithms, because ultimately it's actually a mathematical thing. The pH is a measure of the concentration of hydronium ions in a solution. So the pH is actually the negative log of the concentration of hydronium ions in a solution. I know that sounds very mathematical. So for example, water. As was mentioned, water typically does not react, but it does act like it can react with itself and act as an acid and a base. So when a water molecule donates a proton to another water molecule, notice that you have a hydronium ion produced, H3O positive. And as was mentioned, this doesn't happen very often. In fact, the concentration is 1 times 10 to the negative 7. That's really small, right? What's 1 times 10 to the negative 7? 1, 2, 3, 4, 5, 6. That's 1 times 10 to the negative 7. 1, 2, 3, 4, 5, 6, 7. Yes. That's really small. That's a very small concentration of hydronium ions. So when you take the negative log of that, you wind up with 7. And that is indeed the pH. That describes the concentration of hydronium ions in water, which is just not that there's just not that many of them, and therefore we call water a neutral solution. Okay, more practice with logs. What's the log of 10 to the 2? Right? What's 10 to the 2? 100, right? So essentially it's the power to which the 10 is raised. So 10 to the second, your power is 2, right? So therefore, the log of 10 to the second is just 2. 10 to the 3, What's the log of that? 3. 3 zeros, 2 zeros, 1 0. So log of 1,000, which is 10 to the third, gives you 3. Log of 1, notice log of 1. What is 1? 1 is 10 to the 0. And again, the log is actually the exponent to which the 10 is raised. So therefore log winds up being 0. Log 10 to the negative 7, as we've already done this one, this is the concentration of water. Again, you take that exponent, and it's the negative. Remember, it's the negative log. So therefore, the log of 10 to the negative 7 is negative 7, but then of course pH is the negative log, so therefore you wind up with 7. So with something that's got a greater concentration, so let's think about 10 to the negative 5th. What is that? That's 0, 0, 0, 0, 1. Still a pretty small concentration, but certainly not as low of a concentration as the concentration of water. So therefore we've got something that's got more hydronium ions than water. And 10 to the negative 5th, you take the log of that, that winds up being negative 5. The negative of that negative 5 gives you a pH of 5. And sure enough, that's an acid. An acid is something that's got a pH less than 7. If you have something that has a concentration that is less than the concentration of water. So here we got a concentration of hydronium ions that is 10 to the negative 9th. So it's got a smaller concentration than water. There's very few hydronium ions. You take the log of that concentration, one's going to give you negative 9. The negative of that negative 9 gives you a pH of 9, which is greater than 7. That tells us that that is a basic solution. So here's your range. Remember, water has pH of 7. These are your bases. They've got pHs greater than 7. And these are your acids with concentrations less than 7. I'm sorry, with pHs less than 7. Okay, now with all this information, that was a lot, I understand. Now it's time to get some practice with it. So remember, what is an acid? What is a base? What's a hydronium ion? What's a hydroxide ion? What is a strong acid versus a weak acid? What does concentration mean? All that stuff you'll be required to use that information in order to tackle acid-base solutions. And again, this is a PHET activity. Check out the video. That'll help you step you through all the different parts of the interface. You've probably heard the term acid rain. Acid rain is not quite as much of an environmental threat as it used to be. When I was growing up, acid rain was a pretty hot topic, particularly the area that I lived in, because I lived downwind of a lot of the steel factories in western Pennsylvania. So we got a lot of the blow off from those steel factories. So essentially what happens with acid rain is that sulfur dioxide combines with oxygen in the atmosphere to produce sulfur trioxide. And that sulfur trioxide then combines with rainwater, cloud droplets, in order to form sulfuric acid, which as part of your water, part of the solution, gives you a pH lower than 5. So typically acid rain is any rainwater that has a pH lower than 5. Another way of creating acid rain and acidifying rainwater is because with the increase in carbon dioxide levels in the atmosphere. So you have carbon dioxide combined with water to produce carbonic acid, CH2CO3. And all these things can take a toll on forest land, changing the soil, making the soil more acidic. It also, of course, can have impact on building materials such as limestone. Okay, so as is described on pages 473 and 474, what to do with this acid, what to do with this acid rain? Well, obviously you can reduce the amount of sulfur emissions, carbon dioxide emissions. That will decrease the amount of acid rain that's falling. But there's also kind of another natural solution, which is the oceans themselves, which tend to actually have a pH that is above 7. So the oceans are basic. So when carbonic acid falls into the oceans, there's a certain neutralization that occurs. This can also happen in freshwater lakes and ponds and such. If you have a limestone pond, you're going to have a certain amount of neutralization that occurs. when the carbonic acid combines with a calcium carbonate. You'll have a neutralization that occurs. However, that won't be the case if you have, say, granite as the base of your pond. Then you're going to start to get an increase in the pH of your pond. Okay, we're now to section 21.5, and if you recall, the chapter title is two types of chemical reactions. We've already talked about acid-base reactions. Now we're moving on to the next one. So remember, with acid-base reactions, you had a transfer of a proton. That hydrogen nucleus got transferred from one substance to another. And it was the acid that donated, it was the base that accepted. Now, with our next classification of chemical reaction, we got a different item that is transferred. So these reactions are called oxidation-reduction reactions, and what is transferred, instead of a proton, what is transferred are electrons in oxidation and reduction reactions. So in the case of oxidation, a substance that is oxidized or that undergoes oxidation loses an electron. So for example, here we have sodium. If sodium gives up an electron or loses an electron, that is a process called oxidation. You wind up with a sodium ion, positive sodium ion, that has lost electrons. If you're a substance that gains an electron, that is an object that has undergone reduction or is reduced. So for example, chlorine, this dichloride here, in the presence of two electrons, it absorbs them or gains them, and therefore you wind up with chlorine ions, negatively charged. So the chlorine is said to have undergone reduction. Now, how to remember this? Remember, we had the bad mnemonic device earlier for bases accept, acids donate. Well, here we have Leo the lion went grr. Leo. When you lose electrons, that's oxidation. So lose electrons, oxidation. Gain electrons, reduction. Gain electrons, reduction. Lose electrons, oxidation. So Leo the lion went grr is a good mnemonic way of remembering the transfer of electrons in oxidation and reduction reactions. Okay, consider, if you will, the reaction that produces sodium chloride at good old NaCl. What's actually happening? This is illustrated on page 474 and 475, but essentially you're taking sodium, a solid, and exposing it in the presence of a chlorine gas to produce NaCl. Remember what NaCl is? Remember that sodium is from the far left of the periodic table in the alkali metals, and chlorine is over there in the halogens. And so remember, they form an ionic bond, ionic compound, where essentially the sodium wants to get rid of an electron. It loses an electron. It loses an electron. It loses an electron. It undergoes oxidation. And chlorine, being a halogen and very close to completing its outer shell, it gains an electron. It gains an electron. It gains an electron. Grrr. So that's what's going on there. So in the process of forming an ionic compound, we actually have an oxidation reduction reaction occurring, where sodium is oxidized or undergoes oxidation, and chlorine is reduced or undergoes reduction. So it should be no surprise then that you have your elements that tend to lose electrons. Your Leos are over on this end, on the left side of your periodic table, whereas your GERs, the ones that tend to gain electrons, the ones that tend to be reduced, are going to be on the right side of your periodic table. Now, it is kind of confusing. Your book makes this terminology kind of clear on page 475, that if something tends to be reduced, that means that your chlorine tends to gain electrons, it also facilitates the losing of electrons from the sodium. So it actually acts as an oxidizing agent. It helps the sodium oxidize. And likewise, you could say that, well, the sodium helps the chlorine to reduce. So the oxidizer is considered to be a reducing agent in the sense that it facilitates the gaining of electrons by your chlorine. Now, if you've taken Physical Science 1 and you studied electricity, you understand that electricity is the flow of electrons. So now all of a sudden, we've just talked about materials that tend to lose electrons, right? The Leos of the world, the stuff that can be oxidized. And we've also talked about materials that gain electrons. Things that tend to be reduced. And of course, we talked about things that tend to be reduced are oxidizing agents, and things that tend to be oxidized are reducing agents. But essentially, we're having electrons being produced and then electrons being accepted. They could possibly flow, and if electrons flow, well, shucks, that's electric current. So this should be very exciting for those who are interested in electricity. So it turns out that yes, oxidation reduction reactions are at the core of batteries and fuel cells, and it's described quite nicely on several pages, on pages 476, 477 of your textbook. Talks about the fact that you need oxidizing agents, you need reducing agents, and you also need to be able to prevent a buildup of electrons. So therefore, you need what's called a salt bridge, which allows a rebalance of these different ions so that electrons can continue to flow through your circuit. Okay, so as is described on pages 476 and 477, a battery is essentially just a place where a oxidation reduction reaction is allowed to occur. Essentially, you've got two materials that oxidize and reduce each other. In this case, it's the zinc that gets oxidized. It turns into a zinc ion and gives up or loses electrons. So you have two materials that oxidize and reduce each other, and they're connected by a medium through which ions travel to balance an external flow of electrons. So the electrons are allowed to flow in this direction, and of course flowing electrons is a current. The current helps to light the bulb, and it's the medium then that allows for a rebalance of ions to keep the electrons flowing, to keep them from building up in any particular place in the circuit. In addition to batteries, there are things called fuel cells, which again operate on oxidation reduction reactions. And again, you're welcome to go through the details of the workings of a fuel cell. It's described on page 479 of your textbook, but just the key thing is that you notice that there is an oxidation reaction that occurs here. You have oxidation going on here with electrons being produced over on this side of the fuel cell, and then you have reduction occurring here on this side, on the right side of the fuel cell, because electrons are being gained by these materials. Okay, so we talked about batteries and fuel cells. There's another topic that's discussed in section 21.6 called electrolysis. And electrolysis is when you use electrical energy to produce chemical change. So it's kind of the reverse of a battery or a fuel cell. In a battery or a fuel cell, you allow chemical reactions to produce electrical energy. In a electrolysis, you use electrical energy to produce a chemical change. So it's almost the reverse. One example being in figure 21.23, where you're actually you're running electric current through water, and you're separating the H2O into its component hydrogen and oxygen. So you're producing a chemical change. You're taking water, and out of it you're producing hydrogen gas and oxygen gas. And of course, that's an endothermic reaction. It requires energy to occur. Water doesn't just spontaneously become hydrogen and oxygen. It requires energy to make that happen. Similarly, car batteries run down. In order to recharge your battery, electrolysis has to occur. You've got to run energy into your battery in order to cause a chemical reaction to create products that are then ready to produce electrical energy back in your car. And of course, there's mention of metal ores, using bauxite to produce aluminum. Again, it's a chemical change, and it only occurs because electrical energy is put into the system. Continuing on with the oxidation reduction reaction theme, corrosion. Now, corrosion is an oxidation reduction reaction that occurs within a metal, and quite often it means the breakdown or a deterioration of a metal through oxidation reduction. Combustion is similar. It's an oxidation reduction reaction, but it occurs with a non-metallic material. So we've already talked about combustion at the very beginning of the chapter. I combusted a matchstick. That was wood, right? So cellulose. That was an oxidation reduction reaction that we call combustion. Okay, so we've been through a lot of material, chapters 20 as well as chapter 21. So I indeed encourage you to go through the readiness assurance tests, both in chapter 20. This is the numbers, the questions from chapter 20. You can kind of freeze it if you want to take a look at those answers. And here are the answers to chapters 21's readiness assurance test.